Welcome to my Spacecast, all about welding, where the universe comes to learn about welding. Nah, just kidding. We're working on chapter 43, guys, and I think I put up chapter 46 accidentally. It was a typo. It's chapter 43 for dissimilar metal welding, okay? Just in case. But as always, if you guys don't understand this material, please come at me, talk with me. Let's find out how I can make and explain this, okay? Dissimilar metal welding is really hard to explain, and it really took me a long time to understand. So sometimes you need to think about this and let this roll around in your brain a little bit, okay? The most common dissimilar metal welding is going to be like steel to stainless steel. We're using those same types of properties that the steel has and the stainless steel has so that they can come together, okay? So here we go. So the first thing is that we're joining two different types of metals, metal A and metal B, okay? So we need to find a filler material that is compatible with both. It has a little bit of metal A and it has a little bit of metal B so that we can make them come together. That filler metal is going to have different properties that work with both materials, okay? All right, so really we're just putting two different types of materials together. Hold on, what happened here? It's just doing its own thing. All right, so dilution. Pretty much, dilution is how much of the material can be kind of sucked into the weld, okay? And we need to make sure that it mixes together with the base metals. It doesn't need to be overly mixed, but we need to mix the materials together. Otherwise, it just won't stay. So around, I think, between 8 and 15% is about average dilution. So pretty much, we want to think about it in coffee and sugar, okay? Those of us who afford too much sugar in the coffee, it kind of sinks down to the bottom and it doesn't dissolve. Well, that's kind of the same thing. We need to dissolve this filler metal into our base metal so it stays together so it doesn't crack. That's really what we're talking about. Now, buttering. So any of you who has done pad welding, this will help you out immensely. So really, when we do buttering, what we're doing is we're actually putting a pad weld on the bevel. Now, what does this do for us? Well, let's say I have a material. One material melts at 100 degrees and another melts at 500 degrees. Well, we know that the 100-degree material is going to melt faster and easier, right? So we're not going to put so much heat into it. But it's not going to be enough to get good fusion with that metal that melts at 500 degrees. So what we're going to do is we're going to butter it. And we're going to butter that one that's going to melt at a higher temperature. And then we can even butter the one at a lower temperature. That means I can put a lower temperature with that same filler metal, but I don't have to put it so hot. And then I can join them together so that I can have a nice, evenly distributed filler without worrying that I'm going to burn one side and melt down the other, okay? Or I can just do one side and it worked very well. It really helps a lot. Okay, intermetallic phases. Pretty much it is non-metal and it's almost like glass or little pieces of slag that get stuck in it. Pretty much what it's saying is, oh, hey, you're not the same. And it kind of grows these funny jagged things and it makes a crack. Okay, that's really what an intermetallic phase is, okay? It's because it's not the same and it's all of these little parts in the chemical makeup of the weld that isn't metal. And it's going to make a crack, okay? All right. So what we were talking about right now, weldability, okay? Changing the filler metal as well as the buttering to make sure that things weld together. Galvanic corrosion. So pretty much what this is saying is that if I'm using dissimilar materials, they can electrochemically corrode, like seawater, okay? And it creates this exchange of ions, and it can corrode the less noble material. So really, it's kind of like a 9-volt charge going back and forth of these materials, okay? Because another ion, like seawater, allows it to go back and forth, and it starts to corrode away. So here's like a series in order of nobility. So like maybe if I had aluminum and titanium, and we put those together, the aluminum would be more susceptible to galvanic corrosion, or that electrochemical exchange of ions, and it would corrode. That's really what we're talking about. Okay? Now, when we want to go from stainless steel to carbon steel, this is probably our most common that we're going to see. Okay? So we need to pick things that are going to work together. Oh, come back here. Okay? So we want to look at steels that are going to work together. So we have, let's look at this, 304 or 316 stainless steel. Okay? We're going to look for something like a 309. We're looking at those same compositions. Okay? Now, if we're working with different materials, we're going to use what is called a ferrite number. And really what it tells us is how much nickel is in there, how much chromium is in there, and how ferrous is it. What is ferrous? How much iron is it? And we look at the percentage, and we want to match the percentage with the filler metal that we're going to use. Really, now it's pretty much open an app, look at it, look at a different chart. These charts aren't really used that often anymore, but it's important to know what they're about. Okay, nickel alloys. Of course, we can weld it to carbon steel, stainless steel, copper. Okay, remember, nickel alloys are in 3,000 different types of alloys. So we can have a lot of different ones. But we're also going to look at, Fe, nickel, chromium, iron. Okay, we're looking at all of these things, and we're going to find something that works for both of them. Okay, so it's saying, okay, if I'm going to go to a 304 to an alloy 400, here's some of the ones that I might want to use. Nickel to stainless, right? So they're pretty much relatively the same, but we want to look and make sure that we're taking a little bit from box A and a little bit from box B, so we can make sure that they make C, the compatible filler metal. Okay, so of course, copper to steel or stainless steel. Same kind of thing, except there's not much of a selection here. The most common that you're probably going to see this one is probably like an aluminum bronze or a brass. Okie dokie. So, points to remember, dilution of the base metal is the greatest single factor. We need to make sure that they dilute and work together. We know that buttering joins two incompatible base metals by surfacing one of them or both of them to complete the weld. We know that strength, ductility, and toughness is going to depend on or help us choose the correct filler metal when we're doing this, okay? All right, we know that thermal expansion and thermal conductivity influences service behavior. What does that mean? Thermal cycling. My piece can get larger and smaller. If my material gets larger and smaller and my other material doesn't grow with it, I can have cracking. All right, we know that there can be corrosion resistance issues unless we over alloy. So let's say I have a 316 base material. I'm going to want to use a 316L, which gives me more alloying elements to make it better and effectively give me more corrosion resistance than before. All right, guys, take care as always.